Everyone, thank you for joining. My name is Simone Comensoli, and I am going to present a tool we developed internally at PDF Solutions to track network connectivity in physical design. Over the presentation, we'll look at why tracking connectivity is critical in modern physical design. Then I'll show the key points of the C++ implementation, and I'll briefly show how it could now be easily implemented using OSCrypt and OXPOP. After that, we'll review the tool inputs, the core algorithm, and we'll look at a real-world use case. And finally, I'll summarize the results. But let's get started now with the motivation behind this tool. So semiconductor processes has become incredibly complex, and understanding physical connectivity is more crucial than ever. One of the challenges is that what you see in the layout is not what you get. So meaning that what actually gets, let's say, printed is the result of multiple complex layer operations. As a simple example, consider cut layers. So they break shapes, making it difficult to view the continuity within the layout. For instance, let's say we want to track what is connected starting from the little box I marked in yellow in the picture. One might think that the electrical network connected to the starting point is the one highlighted, but at the intersection between the green polygon and the brown, it is drawn a cut shape for the green layer. Plus, this is a double patterning, and so we have continuity between the green and the brown shapes. As a result, this is the right connectivity path, and this is wrong. Of course, the complexity increases in large designs, making much difficult to identify the networks. And on top of that, there are elaborate stack which defines the interaction between layers. So having a way to track the network in early layout stages becomes relevant. Moreover, when we go from standard cells to top-level hierarchy, the number of polygons involved can easily reach into the order of tens of millions. At that scale, automated connectivity tracking becomes essential. It can, of course, save time by catching problems before they become harder to be fixed. So here a typical example are LBS issues. Those starts from subtle problems like missing vias or misaligned shapes, leading to broken or unintended connections. Tracking connectivity makes easier to identify such issues at early stage, and it also could help preventing errors in the final mask by ensuring that the logical intent is respected. Back at the time we developed this tool, libraries like OXPOP were not yet available, and to keep high performance, we chose to develop it in C++. We then relied in two major C++ libraries. The first to handle the layout data, and the second to perform geometric operations. So the first is the OpenAccess API from the Silicon Integration Initiative, SA2. This provides access to the layout database. We used it to region query from the design hierarchy and also to draw output network polygons. Then we make extensive use of the Boost Polygon C++ library. And Boost allows us to define derived layers using Boolean operators. And it also includes a built-in engine to extract connectivity graphs. These two libraries provide a solid high-performance foundation to our tool. Here we take a closer look at how we interface with the layout database through the OpenAccess SI2 API. And the key component is the OE shape query class, which inherits from the OE region query superclass. This is a very powerful, efficient, and customizable class. We use it to traverse the design hierarchy and extract all relevant shapes. Here we show briefly how it works. So we basically define a class inheriting from the OA shape query. And we initialize the query plugin and the block region query. Then we customize the shape query function to collect shapes in boost fixed 90 objects. And finally, to execute it, we just initialize a new object of the class previously defined, and we call the query function of the OA shape query, passing the design, the layer we want to retrieve the fixed for. Let's now quickly look at how we make use of the Boost Polygon library. So we extensively use it to perform Boolean and geometric operations in order to define the rival layers, which are going to be used later on to define the stack. Here we summarized a list of the most common operations as example. So we have the union, the intersection, the subtract, the keep to select shapes that satisfy some criteria. So in addition, through the connectivity extraction 90 class, we build the connectivity between the polygons. In this function, we build, for example, we pass the polygons belonging to a pair of connected layers, and we use the insert method to insert the polygons to the connectivity extraction 90, and we just call the extract function to retrieve the connectivity between the polygons. After the introduction of the OXPOP and the network extension from SA2, the same functionality can now be implemented using scripting language like Ruby, Python, or Tcl. And in the next slides, we choose to show how it could be done in Ruby. So the libraries involved here are the OpenAccess API and the OSCrypt for the region query part, and the OXPOP for the layer derivation and the network connectivity extraction. So similarly, as described before, we define our own class inheriting from the OA shape query. And we initialize the region query plugin and the block region query. And we define the query shape method to retrieve the OXPOP fix at 90 out of the occurrence shapes. On the right is how we use it. So we just initialize a new myShapeQuery object, and then we run the query method of the OShapeQuery, passing the design, the layer, the bbox, etc. So from there on, we can access the fixed directly from the myShapeQuery object. Here we show how to perform Boolean operations in the fixed extracted using OSCrypt and OXPOP. As an example, here we implemented a simple function to retrieve the fixed for a specific layer for a design. So using the previous defined myShapeQuery class, and then we easily perform the intersect, the union, and the subtract operation on the returned fixed for the layer M1 and for the layer M2 on the design. Next, here is an example about how the network extraction could be performed by using OSCrypt and OXPOP. We defined a main function named extract, and the first thing we do is to define the list of layers and text that are going to form the stack. And we build the stack by connecting pairs of layers via the connect method of the connext90 object. Then we append the polygons by layer purpose pair to the connext90 object. And finally, we call the extract method that computes the connectivity network. So as you can see, in a few lines of code, we can easily perform the connectivity now. So moving forward, let's now look at the three main inputs required by the connectivity tool. Of course, the first essential input is the design layout itself, which is provided by an OpenAccess database, and this includes the raw physical shapes in a hierarchy structure. So as you can see, in a layout of such scale, manual inspection, it will be just not possible. The second key input is the file containing the layer operations. It defines how each functional layer is constructed using operation performed on the raw layers. And the syntax comes from the Boost Polygon library. Here I just show a simple example. So we define metal 1 as the union of two sub layer metal 1 color 1 and metal 1 color 2, each subtracting its respective cut layer. So this level of control is crucial because what's electrically meaningful isn't always directly visible in the drawn layers as said initially. And so we need to define these derivations. So the last input is the stack definition file. Here we define how the layers derived previously interact between each others. And we do so in order to form the technology stack. So each line in this file represents the connection between two derived layers. And the format, as you can see, is quite simple. So we have one layer, a separator, then another layer, like as you see. So we connect metal 1 to contact to poly, etc. This clear structure let the designer define the full vertical connectivity stack. In this slide, we'll give you a high-level overview about the algorithm implemented. All it starts from an user input that is a point and a layer. So this defines the starting point of the net requested. Then if the network isn't already built, we first load the layout and we query all the shapes from it. And we organize it by row layers. This is handled efficiently by using the SI2 OpenAccess API or a shape query. Next, we make use of the boost layer operations to compute derived layers, and we start populating the nodes of a global graph with the polygons. Then for every connected polygon layer pairs that are specified in the stack file definition, we run a connectivity extraction process. As you can see from the schema, this runs in parallel, so meaning that each polygon pairs runs in a separated thread. We then move the edges extracted to the global graph, and now from the node corresponding to the user input, we perform a depth-first search over the connectivity graph to recursively find all the connected nodes. The result of this is a set of polygons that represent the complete electrical net connected to the input. And once we have that, we can move to the final step, meaning drawing the shapes connected. The relevant part here is that the building of the network is done only once. So I wanted now to introduce an example to give you an idea of the timing required by the tool to perform the extraction. We used a design provided by SI2 containing around 50,000 instances. So the logic was generated randomly, but it mimics real-world layout complexity. So overall, the design contains approximately 3 million polygons. Here we just briefly show how the tool works. So in the left snapshot, you see a zoom-in version of the initial user input that is defined by the point where they click and the selection of the layer, which in this case is this dark green, which is metal 3. And on the right, you see the result with the highlight of the polygons belonging to the network connected to the input. In this slide, I break down the execution time of the tool over the test case. So the total runtime is approximately 9 seconds. To open the layout, querying the shapes and deriving the layers, it takes around 3 seconds. Building the full connectivity graph is the most intensive step, and it takes over 5 seconds. So once the graph is built, querying for connectivity from a specific point and layer is extremely fast, under a second, and so it is also drawing the result. Here I reported the characteristics of the machine we used for the test case. The relevant part is the multi-core environment we ran the test case on. So we had 64 cores available for that. So in conclusion, so the SI2 OA region query offers powerful capabilities to extract shapes and instances across deeply nested design hierarchies. And by extending it with Polygon operators through the OXPOP and now with network functionality, SI2 made connectivity extraction far more accessible and intuitive compared with the C++ version we implemented. This results in a practical and efficient solution for both early design checks and also debugging even on large-scale designs. As a next step, we plan to perform a detailed performance comparison between the scripting implementation approach and the C++ based implementation. That brings me to the end of the presentation, and I just want to thank you all for your attention. Thanks.